Right, morning. So today's lesson is going to be all about sigma notation. Now, you would have met sigma before when we did things such as standard deviation in the past in stats. And what you should have known or been introduced to there is that sigma would have been used for something different in terms of the standard deviation. In terms of some formula you may have seen to calculate certain things within stats, this capital Greek letter sigma, so in this form, this is what we use to find out the sum of a series. Okay, so when you see this symbol here, it means we need to work out the sum of. This could be an arithmetic progression, it could be a geometric progression, or it could be neither. It really depends on what type of sequence that you have. So there's a few examples here, and if you look at the first one, so just look at this one that I've highlighted here. So there's quite a bit of notation to get used to. Firstly, on the bottom we've got this r equals 1, and on the top we've got 5. What that means is we need to substitute all the numbers from 1 to 5, and we're only talking about integers here, we're not talking about any numbers in between. So basically there's 5 terms that we need to find and then add them all together. So then in the brackets you've got some function of r. So this is, we've got here 2r minus 3. So when r equals 1, that's the first term, which is minus 1. When r equals 2, that's the second term, which is going to be 1. When r equals 3, 2 times 3, take away 3 is going to be 3, and so on. So what I'm highlighting in green are your first 5 terms. And because of the sigma, it means we need to add them all together. So with only 5 terms, we can simply find out all 5 terms and add them together. But most of the examples we're going to look at today, we might have 20 terms, we might have 50 terms. So there's a lot more to add together. And that's when we want to realize, is this an arithmetic progression? Is this a geometric progression? And then we can use some of the formula that we've looked at over the past couple of weeks to simplify this. Just be careful, not always will your limits start at 1. So if you look at this second example here, we're going from 3 to 7. It might look a little bit clearer in your books than it does on your screen here. So we're starting at r equals 3 going to 7. So that means I'd need to substitute in r equals 3, 4, 5, 6, and 7. And here we have 5 times 2 to the power of r. So the first term would be where we sub in r equals 3. So 5 times 2 to the power of 3, which gives you 40. Your next term in sequence is when r equals 4, that gives you the 80. And then put in your r equals 5, your r equals 6, and your r equals 7. And here, hopefully we can see that we'd actually get a geometric series because we're just multiplying by 2 each time. So as we suggest down here, if you've got a handful of terms, you can probably just get away with just working them out as we go along. So if you just got like 4 or 5 terms, you can probably just sub in r and just find them all and add them all together. But a lot of the time that won't always be the case. You might be going from r equals 1 to r equals 50, as I mentioned earlier. In that case, you want to realize, is this an arithmetic or a geometric progression? Or occasionally, as we'll see in our final example today, there might be a pattern, and you can save a bit of time doing it that way. Now let's jump straight into some examples. So I've got my first example here, and as mentioned here, this is where we've got to find the sum of 20 terms. So we definitely just don't want to find all 20 of them out. First, we want to see what type of sequence this is. So I'm going to work out the first term, so u1. So this is where I just simply sub in r equals 1 to this function that's in the brackets, so the 4r plus 3. So I do 4 times 1 plus the 3, which gives me 7. The second term, so I do 4 times 2 plus the 3, which gives me 11. And the third term, 4 times 3 plus the 3, which gives me 15. Now, hopefully we can see here that this is an arithmetic progression. We're adding 4 each time to get to the next term, so we've got a common difference. So I know this is going to be an arithmetic progression, so I'm going to put AP there. And there's a couple of things now you could do if you want to find the sum. So you know the sequence is going 7, 11, 15, 19, etc. What I'm going to do is jump straight ahead to find my last term in the sequence. So that's just U20. So I do 4 times 20 plus 3 equals 83. So because it's sigma, I need to find the sum. So I need to find 7 plus 11 plus 15 plus 19 all the way up to 83, adding all those 20 terms together. So I want to use the formula that we've been using a lot this week and last week. For the sum of the 20 terms, I want to do n over 2 times a, the first term, plus l, the last term. Alternatively, you could do 2a plus n minus 1 times d in the bracket instead, where d is your common difference of 4. Both ways will work. So I've got my first term, which is the 7, the last term, which is this 83. Sub that all in, and I get my answer of 900. So that is the sum, that's the answer to this. Okay, this would just be 900. As you get used to this, you'll probably realise without having to find out U1, U2, U3 every time. You'll probably be able to notice that 4r plus 3 is an arithmetic progression, but just showing you why it's arithmetic and not geometric or an unknown sequence. So this next one, yeah, again, we've got k this time, so no difference between whether it's k or whether it's r. So we'll find the first 3 terms of the sequence. The first term, so do 3 times 2 to the power of 1, okay, so just subbing in k equals 1 there to find the first term, which is just going to be 6. Just check if there's any questions in the chat first. I'll come on to, I will answer that question about the calculator in a bit, Callum. I'm going to show you how to do it on the calculator later, but I want to go through the theory first, because there is some, it's definitely well worth knowing the theory here. So yes, there is ways that you can do this on your calculator, but I need to go through the theory. So here we can see that this is going to be a geometric progression. So we're just going 6, 12, 24. So multiplying by 2 each time. So this is a geometric progression. So I know that A is going to be 6, R is going to be 2, and N is going to be 20. So I can just use my geometric formula. And then I just find that I have the following answer here. Okay, so quite a big number, as you can imagine, even though 6, 12, 24, the first 3 terms are quite small. Certainly the 18th, 19th, 20 terms are going to be very large. Okay, 2 to the power of 20 is a very big number. So those last terms are going to make this quite a large number in the end. The final example of these 3 is we've got this here. So let's just have a look what happens when we put in the first term. The first term, just get 0.6. The next term, I just get 0.12. And what's happening here is this is just going to be a geometric progression where we're multiplying by 0.2 each time. So yeah, again, it's another example of geometric progression, but this would be a converging sequence rather than diverging sequence, since like we saw in the second one, because each time you're multiplying by 0.2, but it's getting smaller and smaller and smaller, it's converging to a limit. So this is why on top here we can see we've got the infinity symbol. So we are looking at the sum to infinity. And I believe this is where you would struggle doing on your calculator. I mean, I guess you could just put in a large number instead, and it probably will converge to that. But this is where it does help to do it without the calculator. So we want the sum to infinity. So we want to remember that this is the formula that we need to use. And we just simply plug in A, which is our first term. Now the first term is just U1, that's just 0.6. And then the common difference, sorry, the common ratio is going to be 0.2. So we do 1 minus 0.2 because every time we multiply by 0.2 to get the next term. Basically, you can look at that formula as well in the bracket. Sorry, look at the bit after the sigma sign and see that we're doing 3 times 0.2 to the power of k. So that every time we're timesing by another 0.2 to get to the next term. So the sum to infinity will just be, when we put that in our calculator, or 0.6 divided by 0.8, we could probably do that without a calculator, we get 3/4. So if you've got any questions about those, let me know. I will talk about calculators and a little bit later in terms of how we can check with the calculator. The next thing we're going to look at is some proof, and then we're going to look at what happens if we've got to separate some sequences. So we've got a couple of proofs here. This first one, it might look a bit weird because there's no r after the sigma. This is r equals 1, and then we've got n on top, and then we've just got this 1 here, and we're going to show that that just simply equals n. Now, what this is we're just saying that we're going to do the first term of the sequence is just 1. Okay, there's no r there, so it is just 1 on its own. The second term, yeah, again, it's just 1. There's no r there, so it doesn't matter if r is 1, 2, 3, or n. It's just always going to be 1. And what we'll find is we have n number of those. So we've got n number of 1s. So it's simply just going to be n. Another way of looking at this is the first term of the sequence is 1. The last term of the sequence is 1. And we have n number of terms in the sequence. So to find Sn, we would just simply do n over 2 plus the first term of 1 plus the second term of, plus the last term of 1, and this just simply cancels down to n. Using a similar approach, so we can prove that the sum of the r's from r equals 1 to n, so this just means basically 1 plus 2 plus 3 plus 4 all the way to plus n. All we do here is just look at the first term again, which is just going to be 1. Okay, just this time you sub in r equals 1. The last term is just going to be n, because for the last term you're just subbing in n for r. And then in terms of how many terms we've got, yet again, the number of terms is n, so n equals n here. And then just substitute this all in. So first term is 1, last term is n, and essentially that's what this formula is here, except for I've just written n over 2, which is just the same as a half n, isn't it? And then just switch over the n plus 1. So that's just some proofs, and they're good ones they're good results to bear in mind, to remember. Okay, so just if you've just got a single number on its own, you can just simply just say it's 1, or if it was just the sum of all the 2's, for example, it would be 2n in terms of the first, what we're looking at here on the left. And then this is useful for the next bit in terms of knowing the sum of, doing 1 plus 2 plus 3 plus 4, etc. It's just going to be a half n, n plus 1. Now, if we look at example like 3, now there's a few ways we could do this. Now, there is only 10 terms, so technically we could just sub in r equals 1, r equals 2, all the way to 10, and we could then just add those terms together. But subbing this in 10 times is going to be quite time consuming. What we'll find out is if we find u1, u2, and u3 here, that this isn't going to be an arithmetic or a geometric progression. We won't find a common difference, we won't find a common ratio if we just look at the whole of what's in the brackets there. So what I'm going to propose we do is that we split this up. So I'm going to split this up into working out the sum of 2 plus 3r, and then working out the sum of the first 10 terms of 4 to the power of r. And we can do this with a series like this, with the sigma like this. We can just simply split it up into individual terms. So we can either deal with it all as one, or we can split it up like this. If I wanted to, I could split this up further and look at the sum of the 2's plus the sum of the 3r's plus the sum of the 4 to the power of r's. But I'm just going to leave it as 2 things to work out here. Again, if you've got any questions in chat, please let me know. I am doing quite a lot of talking today because there's quite a few examples and I don't want this to go over half an hour. So apologies if I'm doing a bit more talking and not asking you as many questions today. It's just there's quite a lot of examples to get through. There's quite a lot of different ways they can go in the exam with this. Now, I'm going to start with the left-hand side here, or the left term. So firstly, I can find u1, which is going to be 2 plus 3 times 1. So I'm just subbing in r equals 1 into 2 plus 3r here. So that's 2 plus 3 times 1, which is going to give us 5. The second term, that's going to be 2 plus 3 times 2. That's just going to be 8. And then u3, well, that's going to be 11. And we can just see that this is going to be an arithmetic progression. So I can just use the formula that's appropriate for this. So A is going to be 5. The first term is going to be 5. The 10th term, the last term, so 2 plus 3 times 10, that's going to be 32. And n is just number of terms, that's going to be 10. So I want to find out the sum of the first 10 terms. And we just simply work that out. And I get 185 when I do so. So now separating this into the next part of this, I'm just going to move this along so it doesn't get mixed up with the other parts. So now we'll work out the sum of the 4 to the power of r's. And yet again, you might be able to spot whether this is arithmetic or geometric right away as you get used to this, but just in case, I'll just show you why it's geometric, not arithmetic. So we just do 4 to the power of 1, which is 4. The second term, 4 to the power of 2, which is 16. Third term, 4 to the power of 3, which is 64. So you're multiplying by 4 each time to get to the next term. So there's a common ratio of 4. So the first term is also 4, and n is going to be 10. So use a times 1 minus r. Remember, you can actually do this r to the power of n take away 1 rather than 1 take away r to the power of n, as long as you'd have r minus 1 on the bottom instead. But I'm just using the version where I've got 1 minus r to the power of n on top and 1 minus r on the bottom. When I do that, I get quite a big number here. And then finally, I could just write out what my final answer is. So I just simply add the 185 and the 1,398,100 together. And I just get this answer here. Okay, that's going to be my final answer. Okay, just quickly check the chat. Is there any questions here? If not, we'll move on. This next part then, you've kind of already seen a question where you have to use this skill. And I know from marking the assignment, which had this particular question on, this question 4 that you can see on your screens now, that this was quite a lot of mistakes that were made on this question. So the question that you had in the assignment, I'm not going to go through that question again, But in that question 2, you're asked to find the sum of the 21st to the 50th terms, inclusive of the progression that you had in that question. So if you're finding the 21st to 50th terms, you want the 21st term in there, 22nd, 23rd, all the way to the 50th term. What a number of people did was they found the sum of the first 50 terms, which was good, and then realized that, well, we don't want all of the terms before 21. But what a lot of people did was they took away the sum of the first 21 terms. Now that's incorrect, because if you take away the sum of the first 21 terms, you'd be taking away that 21st term as well, but you want to include that. So this is why when we have this formula here that you can see in the red box, when we're finding from, if we've got our first term is going to be r equals m and we're going to n, what we want to do is just find out the sum of all the terms from r equals 1 up to n, but then take away all the terms that we don't want. But the key thing here is we've got this m minus 1 here, because we don't just want to go up to m, because we want that term, if you will. So in that example there, we do the sum of the first 50 terms, but then we take away the sum of the first 20 terms because we want to include 21. If we take away the sum of the first 21 terms, we'll be taking away that 21st term as well. Let's have a look at a couple of examples and then we'll get straight into some past paper questions. The first one, now I think we've seen quite a few of these examples now to know that this is actually going to be an arithmetic progression. So I'm going to look at that and just think, well, that definitely is an arithmetic progression. I've done enough examples like this to know that that is going to be arithmetic rather than geometric. But if in doubt, just sub in some values and check that it is. Now I'm going from r equals 100 to r equals 200. So what I need to do is find the sum of the first 200 terms, and then I want to take away the sum of the first 99 terms. Okay, there's a 100 here, so I need to make sure this is 99 here, because I don't want to take away that 100th term as well. So first I'm going to find the sum of the 200 terms. So in that case, a is going to be 3. That's the first term of our sequence. Just sub in r equals 1, 2 times 1 plus 1. The last term of the sequence is when r equals 200. So 2 times 200 plus 1 is going to be 401. And then n is going to be 200. There's 200 terms. So I'd do 200 divided by 2 times the first term plus the last term. Now, by the way, a lot of these examples I'm using a plus l in the bracket. Yeah, again, if you want to use a plus n minus 1 times d instead and do it that way with the common difference, that's absolutely fine. Sometimes you might have to do it that way. Anyway, I'll work that out in a second. But for the sum of the 99 terms, yeah, again, a is 3. The last term would do 2 times 99 plus 1 for 199. And then n is 99. Okay, it's 99 terms. So to work that out, we'd do 99 over 2 times the first term plus the last term. And then simply, we take the first 200 terms and take away those first 99 terms. And we get 30,401 when I do so. The next example, and again, check it if you're not sure, this is a geometric progression. So you could sub in k equals 5, k equals 6, k equals 7, and you can see that there is a common ratio there. So this is a geometric progression. Now in this question, I need to do the sum of the first 12 terms, take away the sum of the first 4 terms. Remember, we don't want to do sum of the first 5 terms because we don't want to lose that 5th term here. I have a first term, which is just going to be 5. That's just found by simply substituting in k equals 1. So I do 5 times 3 to the power of 1 minus 1. So 5 times 3 to the power of 0. That's just going to be 5. The common ratio is just going to be 3, because every time I have to multiply by 3 to the power of something. So every time I increase the power by 1, you're multiplying by another 3. Yeah, again, if in doubt, sub in K1, K2, K3, find that common ratio out for yourself. So I'm going to find the sum of the first 12 by doing 5, the first term, 1 minus r to the power of n over 1 minus r. Find the first 4 terms by doing 5 times 1 minus r to the n, so 3 to the power of 4, over 1 minus 3. And I get the following numbers when I do so. So the first 12 terms come to 1,328,600. The first 4 terms just come to 200. And when I work that all out, I get 1,328,400. Right, just give you a second just to take that in, ask any questions that you may have. And then we'll get into these past paper questions. Apologies, this might go over a little bit, go over the half an hour a little bit. Past paper question exams aren't too long, so we should hope to be done in the next 10 minutes at least, at the very most, sorry. And say apologies, I've not really asked you many questions today. It's just that there is quite a lot to get through. Past paper question time then. A sequence of terms u1, u2, u3 is defined as un equals 2n plus 5 for where n is greater than or equal to 1. And we're given this following information, as you can see below. And we're asked to find the value of this capital N. So basically, the number of terms required that for 2n plus 5 for all of them, all the terms to add up to 2,200 basically is what we've been asked to find. Now, our sequence goes 2n plus 5. That is going to be an arithmetic progression because basically your first term is 7, then the next term will be 9 as you sub in n equals 1, n equals 2, n equals 3, and so on. So we know it's an arithmetic progression. We know a is 7. We can't find the last term here because we don't know how many terms there are in the sequence. That's what we're trying to find. We're trying to find n, trying to find the number of terms in this sequence. So we need to rely on there being a common difference, which is just going to be 2. Okay, that's just the number in front of the n there, as you know from nth terms from GCSEs. But yeah, again, just do u1, u2, u3 if in doubt to find your first term to find your common difference. And you know the sum of these terms, so Sn is going to be 2,200, okay, because you've got the sigma there. And if you're adding up all these terms and it's come to 2,200, well, that must be your sum. So we're going to use, I'll write out the formula that we are using here. So we're using the summation formula in this version. So we're using a plus l a lot today. But we're going to use this version instead because we don't know what the last term is. And when I do so, you've got this, I'm just going to replace this lowercase n with a capital N here, because that's the number of terms I've got in the sequence, this capital N, which I'm asked to find. And then we've got 2 times a, so 2 times 7, plus n minus 1, yet again, I'm just going to replace that lowercase n with a capital N. Common difference of 2. And I know that has to equal 2,200 because the sum has to add up to that. With a little bit of simplifying and multiplying both sides by 2. In this bracket, I've got 14 plus 2 times minus 1, so I've got the 12 there. And then I've just simply got 2 times n. So I've got 12 plus 2n in the bracket. And then I'm just going to multiply both sides by 2 to get rid of that n over 2. There'll be a number of different ways you can rearrange it. This is just one of them. And with rearranging, we get to this stage. I can then just simply divide by 2. You might not fancy factorizing this one, so if you want to reach for your calculator, you can do. If you can't, see right away that 44 times minus 50 is going to be minus 2,200, and those terms add together to give you your 6n there. So then just put that in your calculator, find that n equals 44, n equals minus 50. Now obviously we don't want to include the minus 50 because it's got to be positive. So n equals 44 is just the answer here. You can pop any questions you've got in chat. And then we're just going to look at 2 other examples. They're quite short, but they're a little bit different. So I really want to show you these examples. So worth hanging around for these examples because they're quite different, these ones. They can catch people out. We should hopefully see a few more of these in the next lesson. We do some recurrence relationships as well. But these ones are well worth having a look at, these next 2 examples. So this question is only 2 marks, but just a little bit different. So we want to get our head around it. So express the series 2 times 3 plus 3 times 4 plus 4 times 5 plus 5 times 6 plus 6 times 7 in the form as given there, where the function of r and a are to be determined. Now I know, looking at this, the first term here is going to be r equals 2. So where I see 2, I can just think of that instead as r. So what does that make 3 then? Well, 3 is simply 1 more than 2. So I can call that. So I can think of the first term of the sequence as being r times r plus 1. And then the next one would be r plus 1 plus r plus 2. And then I'd have r plus 2 times r plus 3, and so on. So if I'm starting at 2, then I know if I sub in r equals 2 into here, well, that's just 2 times 3. That's what I've got here. So it must be that my function is r times r plus 1, because, check that this works. When you sub in r equals 2, you get 2 times 3. That's the first term. If you sub in r equals 3 the next term, you get 3 times 3 plus 1, so 3 times 4. Then you get that second term there. And then so on when you put in r equals 3 and carries on. We need to put a number on top here as well. So we need to find what a is. And that's just simply going to be 6, because the last term in the sequence is, well, we've got 6 times 7. And to get that, we'd have to put in r is 6. Then if you do r plus 1, you get 7. So then this is our answer. Okay, we've got, this is going to be a, and this is going to be fr. If we just want to make this clearer, we could say fr equals r times r plus 1, then a equals 6. So short question, but want to go through that one because it is maybe a little bit more unusual than some of the other ones. It's not an arithmetic or geometric progression here, because if you look at the terms, we're going 6, 12, 20, 30. There's not a common ratio, there's not a common difference there. Final example then, we've got a sequence begins 1, 3, 5, 3, 1, 3, 5, 3, 1, 3, etc. and continues in this pattern. Find the 55th term of the sequence showing your method. Yet again, this is not an arithmetic progression, it's not a geometric progression. So we need to just carefully look at the terms and just see what's happening with this sequence. Now, it's what we call a periodic sequence, because you should notice that this just simply keeps on going 1, 3, 5, 3, 1, 3, 5, 3. Okay, so hopefully you can see that pattern there, which is just going to keep continuing. So each cycle, if you will, has 4 terms. So what I would do is I'd do 55 divided by 4. So I want to see how many cycles I'm going to need to go through. So if I do that, now your calculator is going to say 13.75. this is one of the rare cases that we don't actually want to think of this as having a put a decimal at the end, or put a fraction on the end, or write it as an improper fraction. We actually want to go kind of back almost like primary school, and we want to put a remainder here instead. So we want to think of this as, well, 4 goes into 55 13 times, but with a remainder of 3. And the reason we want to do that is, as I go around in this cycle of 1, 3, 5, 3, I can think of it as, well, 1's always the first term of the cycle, then we've got 3's the second term, 5's the third term, and 4 is the third term. So 13 times 4 is 52. So after 13 cycles, I'm back to beginning. Okay, so after the 52nd term, I'll then go back to the beginning. So the 53rd term is going to be a 1. The 54th term is going to be a 2. And the 55th term is going to be a 3. So the 55th term did I say 3 before? I meant to say 5. Okay, the 55th term is going to be a 5. Okay, because it's the third one in that, because the remainder 3 is the third one in that cycle. Finally, find the sum of the first 55 terms in the sequence. And yet again, it's about noticing these cycles. I've got 13 cycles, as I found out in the first part. I've got 13 cycles of 1, 3, 5, 3. So I'm going to add that together. So every time I complete the cycle, it's going to all add up to 12. Now I've got 13 cycles of 1, 3, 5, 3. So I need to do 13 times 12 for 156. Okay, that's because I've got 13 cycles of 1, 3, 5, 3. Then I've got the 53rd, the 54th, and the 55th term. So that's just going to be a 1, a 3, and a 5, which is going to give me 9. So for the sum of the 55 terms, add your first 52 together. That's going to be the 52 terms, and then add your 53rd, 54th, 55th term on to add that 9 on. And that's going to give you 165. Apologies, going a little bit longer than normal. Make sure that you have a look for the questions today. To be fair, whilst you can get some quite tricky ones here, there hopefully you find there's some quite nice questions today. But please do ask for help if you're not sure. Please ask us to help any ones that you've been stuck on previously. Make sure that you have